So we're going to start our next sort of topic, next paper. So last few lectures, we talked about two papers mainly, the SL equals L paper due to Reingold and the zigzag product paper. And we use that as an excuse to learn a little bit about spectral graph theory. And today we're going to see spectral graph theory again. And here we will use spectrum to infer some other property about a graph. Okay? One particular graph, we want to say something, and we will use spectral properties to prove that. Okay. And why is this particular graph theoretic statement interesting? That comes from this long-standing conjecture called sensitivity conjecture, and I'll talk about that first. Okay. And we'll connect back to spectral graph theory. So the second chapter, this new thing is on a new whiteboard. So you can find the link to the new whiteboard also on the class website. So we finished zigzag product, how to analyze it. And then we saw how to get in log space using zigzag product. And then we also talked about expander graphs and how you can construct them using zigzag product. Okay. And today the goal is to talk about what is called the sensitivity conjecture. And measuring complexity of functions. Okay. And should also remind you that midterm 1 will be up on Gradescope tomorrow at 6 p.m. Okay. So it'll go up tomorrow at 6 p.m. and you have 48 hours. So it doesn't mean the exam is going to take 48 hours. Some of you asked, it's really not that long of an exam. If you want, you can just read the paper problems quickly to, maybe think about it over the time, but it shouldn't take the entire time. It's just a window for you to find time to do it, okay? And don't anticipate it taking more than a handful of hours, if at all, right? And upload solutions. Great. All right. Okay. So let's now talk about sensitivity conjecture. And so up till the first 5 lectures, the main objects that we were studying were graphs. Now we're going to study functions. Okay. In particular, we will talk about Boolean functions. Okay, so Boolean functions mean the inputs are n-bit strings and the output is either 0 or 1, right? So these are discrete functions in that their output is only one of 0 or 1, okay? And their goal is to relate various measures of complexity of these functions, okay? All right. So we're going to talk about measures of complexity. Okay, measuring complexity of F. Okay, so one way to think about it is, just imagine the function is once again sitting in the cloud, and or the code for the function is sitting in the cloud, and you get to interact with the cloud to compute f of x. Okay, so you have the input So you have some limited access to the input and you're trying to figure out what is f of x. Okay, and you want to measure complexity in terms of how you use this resource. All right. Okay, that's very high level, very vague. And of course, that means that there are many, many different ways of measuring complexity. Okay. So one common measure that you might have seen before is what's called the decision tree complexity. Okay. So what is decision tree complexity? So a function is like a decision tree, meaning, I query or look at the value of some variable, maybe let's say x10. Okay, so I have some input x, which is x1 through xn, and I'm trying to compute f of x. And the algorithm for computing f of x is, okay, look at the value of x10. If it is 0, then you query x5. Check the value of x5. Okay. If it is 1, maybe you check x3. And again, if it is 0, maybe you check x1. Maybe if it's 1, you check x3 again, and so on. Okay. So you adaptively query variables based on what you learned so far. And at some point, you say, okay, the answer is output 0. Output equals 1, and so on. Okay. It's a very simple but also popular model because they're very interpretable, right? So you can think of your grades maybe something like, okay, is it more than something? Then you get certain grade. If it's less than something, then you go to certain grade, and so on. Okay, so you can think of all of those things as decision. All right. So a fairly common model of functions that arise in various applications. Like, for example, in control systems and so on, you see them all over the place, right? Now, how can it define complexity? Well, one way to measure complexity of a function is if the function has a small depth. Maybe you only have to query 3 variables or 4 variables to know the value of the function, then that's a simple function. Okay, so that's a measure of quantifying how simple a function is or how complicated a function is. Okay, so the decision tree depth of a function is the minimum depth of a decision tree that computes f. Okay. For every function, there is a decision tree. For example, I can have a full binary tree where I start from x1. If it is 0, go to x2, then read x3, and so on. So that will have depth n and 2 to the n leaves. But some functions might have much smaller or shorter decision trees. Okay, in particular, we're looking at the minimum depth of a decision tree that computes f. Yeah. I mean, it's one measure. You can also talk about the average depth and so on, but minimum is kind of saying that minimum over all decision trees. Maybe I should qualify this. It's both. So you take the max path and then that's the depth. And then minimum is across all the decision trees computing it, pick the one which is the simplest. Okay. All right. So it's a good measure. And let's look at some functions. Right. So we have the OR function, which is just going to output 1 if any of the bits is a 1 and 0 otherwise. So what's the decision tree complexity of OR? Any guesses? What's the smallest depth decision tree to compute OR? Yeah. Not quite. Because So the way decision trees work, one thing that's important about decision trees is you have to decide which bit to query before you know what to query, right? So let's say I query x1. Now, if it is 1, I know the answer. You say output 1, okay? But if it is a 0, then since I was drawing ones to the right, so let me stick to that convention. Okay, so here I know the answer, so I just output 0, okay? But if it is a 0, then I still don't know the value of the function. I have to query x2, okay? And then if it's a 1 again, I know the answer, but if it is a 0, I have to keep going, right? So all the way, you have to basically query every bit. So these should be 1s, sorry. You're outputting 1 in these cases, okay? So there is a path, where until you see all of the bits, you don't know the value of the function. Okay? So the decision tree complexity of R is n. Said every function has decision tree depth at most n. You can just build a full binary tree and have the labels accordingly at the leaves. For R, it is actually n, even though it's a seemingly simple function. Okay. And the same thing for AND. Okay. Any questions? On the other hand, there could be other functions which are seemingly more complicated, but could be simpler as decision trees. So for instance, I can look at the full binary tree where, let's say, n is a power of 2, like 2 to the k. Then I look at the middle bit, and then okay, so look at the middle bit, and then the middle bits in the 2 halves, and then the middle bits in the remaining halves, and so on. Okay, it's just a full binary tree. And then, maybe at leaves, you have some labeling to output zeros and ones. Okay. So once you see the leaf, you say, okay, this is a 0. Here you output 1. Here you output 0. Here you output 1, and so on. Okay. So this is not a single function. There's a whole family of functions, but all of these functions have decision tree depth at most log n. Right. So the depth is log n base 2. Okay. And the function, on the other hand, depends on all n bits. It depends on all n bits, but the depth is only log. Yeah.
Wait, so I think kind of mystical. Like, what's the point of this tree? I guess like what's happening.
So I'm saying it's just you can put any labeling there, and you would still have small depth.
Oh.
Okay, it's a class of functions which has small depth, and nevertheless, the function depends on all n bits. So the depth is only log n. Right? On each input, somehow the value is determined by only log n variables, but which log n you don't know. Okay, yeah.
Wait, how can it be a function of all n bits if you're only looking at like log n of the bit?
So let's say you don't know some bit, right? On a specific input, it only depends on log n, but which log n could depend on the input.
Okay, it's kind of like non-deterministic.
Exactly. Yeah. We'll talk about, we'll talk about the measure which allows for that in a second. But here the point is decision trees are kind of deterministic, right? You need to know, there should be a way to figure out which variables are important. There's like an algorithm to do that. Okay. And one more nice example to keep in mind, which is not exactly the same thing, but is related, is called the indexing function. Okay, indexing function is basically like, you have an array and you have an index and you have to map into that index, that array, sorry. Okay, so the input is kind of broken up into two pieces. Okay, so you should think of it as, so n is a power of 2. Okay, it's a function which takes k plus 2 to the k bits and then outputs 0 or 1. We will view the k plus 2 to the k as k bits and then followed by 2 to the k. All right. And why is it called indexing? Well, you think of the 2 to the k bits as an array. Okay. And then the first k bits as an index. So this is A, and this is, let's say, X. Okay. So f of I comma x is xi, where, you read the ith bit of x viewed as binary. Okay. So I have a bit string from 0, 1 through k. I can view this as a binary encoding of an integer, and I just look at that position. Okay. So this is a function. You can write it as a decision tree. What do you think is the decision tree depth of indexing? K plus 1. Okay. So once again, it's a function which seems complicated, but its decision tree depth is fairly small. Okay. Why is it only k plus 1? Well, you basically look at the bit representation of I. Right, so you have the first k bits. You kind of basically look at the bit representation. And then here, if this is the all 0 string, you just branch on x0 next. So here, read xi at the ith. Okay. So like here, you would branch on x0, maybe here on x1, here on x2, so on up to x2 to the k. Okay. And you output 0 or 1. Okay, so indexing is a function which again depends on every single bit, but its decision tree depth is small. All right. So there's a related measure which we call certificate complexity. All right. So certificate complexity is okay. So let's think of the OR function, right? Its decision tree depth is high, is n, but we don't think of it as a complicated function, right? There's really only one input which requires you to go all the way. When the input is all zeros, you basically have to read every bit to know the output of the function, right? For example, it's easy to certify that the function evaluates to 1. What do I mean? Suppose I tell you that here's my x, r of x equals 1. How can I prove to you that r of x equals 1? Of course, I can send you the entire input x, And you'll say, of course, I can compute the function, but do I need to send the entire input x to you to certify that R of x equals 1? No, I could just send a single bit, right? So in some cases, I could I don't have to send in the entire input for you to know the value of the function, okay? So that is what certificate complexity is supposed to capture. How many bits of x should, imagine I have x and you know the value, you know how to compute the function f. How many bits of x should I give you so that you are 100% confident of the value of f of x? Okay. So minimum over all s such that s is a, I'll define this in a second, certificate at x. Okay. So what does certificate at x mean? Means that it's a subset of all possible coordinates such that knowing x at s fixes the value of f of x. Okay. So if R of x equals 1, for example, I can send you the first bit, which is 1, and everything else doesn't matter once I know that this bit is 1. The value of the function is already determined. Okay. So we can think of it as S is a certificate for X if, this is for a specific function. X and Y agree on S, f of x equals f of. Okay. All inputs which agree with me on these coordinates have the same value. So it suffices for me to just send these values and not worry about the entire. Okay. Any questions about the definition? It's basically like saying, to compute f of x, there may be a lot of irrelevant coordinates. You just need to know these coordinates and you know the value of the function. What is the smallest number of coordinates? That's the certificate complexity of f at x. S is a subset of indices, yeah. Exactly. Yeah. So this is just the coordinates of S. So you have the entire X, right? Now I'm looking at X restricted to the coordinates in S only. Okay, and I want to say, as long as X and Y agree in these coordinates, okay, if they are equal, then even if they differ in the other coordinates, it doesn't matter. The value of the function is the same. Okay. So for example, what is the certificate complexity of R at, let's say, 0, 0, 0, and 1? This is my X, this is my function. What is the certificate complexity? Just 1, right? In certificate complexity is just the size, right? So if I know the last coordinate is 1, the value of the function is fixed. No matter what you do to the remaining n minus 1, you don't have to tell me those things, okay? If this is my x and the function you're trying to compute is r, but just say, okay, xn equals 1, that's it. The function's value is fixed, okay? So this would just be 1. Right? Yeah? this case, like look at like half of the, it's like half plus one of the bits, then you know that it's there. But for that, you need to know what n is. We do know n. So here it should be like or n. Yeah. Okay. So we're thinking, you know n and you also know the function, right? But what you imagine that x is kind of the unknown, and you're trying to compress x so that you know the value of f of x without too much information. Okay. Yeah.
The output instruction should be like S, right? Or is it just that?
Just the size.
Just a size.
Just the size. Because there can be many sets. We're only interested in how big is the smallest certificate. Okay. Yes, as long as in fact, CC of or of, that's a good question. Even if I put 1, 1, this is also just 1. Because even though there are 2 ones here, I don't care. Just tell me 1, 1, the value of the function is fixed. Okay. But what about certificate complexity of R at all zeros? What is this? N, right? Because unless you see everything, the function is not fixed. Okay. So certificate complexity is a more fine-grained measure. It's basically saying somehow, okay, there's one input where it's n, but most of the other times it's just 1. Okay. And there are ways to measure kind of average case at, certificate complexity and so on. But let's even talk about the worst case measure. Okay. So now for any function f, the certificate complexity of f is the max over all inputs of f comma x. Among all of the inputs, whichever input has the largest certificate complexity, you look at that. All right. So CC of R would once again be n. Okay, just like decision tree complexity, this is another measure that we just introduced. All right. And as you were actually mentioning, let's also do the example of majority. Let's say n is odd and of x equals 1 if as many ones, at least as many ones as zeros and 0 else. Now, what is the certificate complexity of majority? Yeah, let's say n is odd. N plus 1 or 2. Okay, because if it is a 1, you just have to show me those many coordinates which are 1. The rest don't matter. Okay, at least factor of half, say it. The decision tree complexity of majority is actually n. Okay, there's no way you can save on the decision tree complexity without reading all of this. Okay, so these are ones. Basically, it can happen that you have everything 0, 1, 0, 1, 0, 1, 0, 1. This is the last bit which is changing, right? If you don't read that bit, then you're in. It requires a proof, but it can be done. All right. So now let me ask. Okay. So typically we want to relate various complexity measures, right? So we already have 2 measures, and there's a whole taxonomy of measures. We'll talk about them in a second. Why do we have this taxonomy? Because these things show up in various applications, right? Initially, they were introduced because people were interested in functions, circuits, but then people realized that they kind of show up in understanding parallel computation, understanding various properties of functions from an analytical perspective, and so on. Okay. So the origins are very different, but they keep showing up in various places with some applications. So, they're interesting. Okay. But what we're going to see is very beautiful and succinct. So I don't want to go too much into the original motivations, okay, because that'll take too much time, right? Okay. So how do we relate these measures? Okay, so far we have two measures, CC of F and DT of F. Which of the two do you think is smaller, bigger, or do you think they're comparable most of the time or not comparable? What do you think? Take a guess. Like, let's say, a function has small decision tree. Can you control the certificate complexity?
Should this certificate complexity be always less than equal to?
Okay, so let's see if that is true. So hypothesis is this. To prove this, you need to show that if there is a decision tree of certain depth, then the certificate complexity is small, right? Yeah.
So like, that's these kind of, if you had the powers like for you, your decision tree, that's like.
Sort of, but the thing is certificate complexity is somewhat adaptive, right? The set that you pick can depend on the whole X. Whereas decision tree, somehow you have to figure out the set a bit at a time. There is some adaptivity too, but it's not like it's not a global lookup. Right? You read the first bit without any information, right? The root, what you read there is fixed. And then you get some flexibility, okay? So intuitively, decision trees seem more limited than certificate complexity, okay? And in fact, that is true because suppose I had some tree like this. There's a question with respect to an input. It is defined for the input X, but for the function, we look at overall max. Okay, so we first defined it for an input, and then for the function, we look at the max. Okay. All right. So suppose you had a decision tree like this. You have decision tree of depth D, and then you have the leaves where, you have 0 output here, 1 output here, and so on. Okay. So if the depth is D, my claim is that, in fact, certificate complexity is at most DT of F. So you need to show that for every X is less than or equal to D. That on any input X, there are D values. If you know those values, the value of function is fixed. What would be those D values? Any guesses, suggestions? Exactly, right? So you look at what path gets picked on the input X, right? So, it's maybe this path, right? And if it is that path, then knowing all the variables on that path will fix the value of the function, because if those values are the same, that is the path I'm going to take, right? If the path is x10, x1, x11, then it doesn't matter what x5 is because I'm exactly following that path. Okay. So because the variables on the path taken by X are a certificate. Okay. Okay, this is a simple observation. Maybe it's not too surprising that certificate complexity is smaller than decision tree complexity. Decision tree, of course, is more rigid, right? Because somehow you need to know which variable I'm going to query, and that immediately tells you which variable. Okay. But certificate complexity, you get to pick the set as kind of arbitrarily, right? And how about the other direction? Do you think there should be a comparison, dt of f and cc of f? It turns out that there is, in fact, a very surprising connection even in the other direction. Okay. So decision tree seems way more limited than certificate complexity, but there's a very beautiful theorem that, in fact, decision tree complexity can't be much higher than the certificate. This is very remarkable because when we talk about certificate complexity, it's like saying for every X, there is some set. There is no structure in these sets at all, right? It could be, maybe the certificate for X is the set 135, right? First X. Maybe for some other X, it is 10, 13, 14, right? But if you go back to decision trees, somehow the paths which are used as the certificates have a lot of overlap. In particular, there is a variable which appears in every certificate, the root node. Okay, so that's why this is very remarkable that such a thing is true, but it is true. And this was, I think, proved. It has been proved multiple times without people realizing that they're proving the same thing. Maybe the first time was in the 70s or 80s. Okay. And it also gives you a way to kind of construct decision trees when you don't know that those things exist. Yeah.
Is there a really easy one that's like the same number of depth for each?
So we'll talk about a function which does have this gap actually. So now parity is bad even for certificate because you need to say everything unless because the one single bit can flip everything, right? But yeah, if you were to write it as a decision tree, then there are things where you really have to see everything. Okay, this quadratic gap is important. We'll look at an example soon. All right. Yeah. Yeah. So let me introduce other measures and then we'll look at examples. Okay. Right. So as I said, it's a very beautiful theorem and surprising in some sense, right? Because certificate complexity says that for every X, there is some set which is small and certifies the value. But decision tree is really saying that these sets are kind of structured. They're coming from this binary tree or something, but there's nothing like that in certificate. Okay. All right. So let me introduce another measure, which is actually called sensitivity. And that's where the sensitivity conjecture comes in. Right. So at any point X, sensitivity measures how sensitive the function f is at X. What do I mean by that? A function is sensitive at a point if somehow, let's say you make a mistake in one coordinate of X. Does the function's value flip? That means the function is sensitive at that point, right? So that's what this is trying to measure. Like, for example, if I have R, but my input is half ones, then it's not very sensitive. Even if you flip a single coordinate, the function doesn't change at all. Okay. So sensitivity measures okay. Look at how many coordinates are there such that flipping that coordinate changes the value of the function completely. If there are many, many such coordinates, then the function is very sensitive there. right? You have to really know every coordinate. If you miss any of these coordinates, the function gets screwed. Okay. Right, so this can again depend on the input that you are at. Right, and just as before we did for certificate complexity, we can define the sensitivity of a function as this guy. Among all of the inputs x, pick the one which has the worst sensitivity. If there is a point where flipping any of some k coordinates flips your function is at least k sensitive. Okay. All right. So there's also a graph theoretic way to view this function, and that's the following. Okay. Now, we're going to define an important graph, important because it shows up in many places. And this is the graph, which is a hypercube. Okay, so denoted HN, it's a graph on 2 to the n vertices, right? So the vertices are indexed by strings of the form 0, 1 to the n, right? And for example, this is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, and 1, 0, 0, 1, 1, 0. Okay, I'll tell you how the edges are drawn, but the vertices are just elements of 0, 1. So this is H3. Okay. And two vertices x comma y are adjacent if they differ in a single coordinate. Okay, so two strings are connected if they differ in exactly one coordinate. So 0, 0, 0 is connected to 0, 1, 0 because they're different in exactly one, and so on and so on. So this is what gives you this exact graph. Right. So now, you can interpret sensitivity in terms of this graph as well. Okay. So what is that interpretation? So imagine I have my hypercube as usual, but now given a function f, I can imagine coloring the vertices according to f. If f of x is 0, let's say I color it with the red color. If f of x is 1, I color that vertex with blue color. Okay. So then sensitivity is just the max over all vertices x of the number of neighbors of x of opposite color. Okay. So imagine for every vertex, I colored according to, okay, so this is orange, orange, orange. Okay, let me do it
So it has some meaning.
Okay, so let's say green means f of x is 0.
Okay. And red means f of x is 1. Okay.
Then the sensitivity is you take any vertex, check how many of the neighbors are of opposite color. Right? Because if they're opposite color, just means that means that flipping one coordinate change the value of the function. It's just a graphical representation of the same definition. Right now, it's just tautologically the same, but it will give us some nice statements to understand later. Okay. So for this function, for instance, the sensitivity would be what? 3, right? Because, for this vertex, for instance, all 3 of its neighbors are of the opposite color. Okay. Now, so far, we had this things. We haven't proved this, but at least we stated them. Right, so we had CC of f, we had dt of f, and then we knew that this is at most CC of f squared. Okay. Where would sensitivity go in? So we have a new measure, sensitivity of f. How does that compare to, certificate complexity, to decision tree complexity, CC of f, and so on? Any guesses? How does certificate complexity compare to, let's say, CC of f? It's smaller, right? Because somehow, if I don't change a coordinate in the certificate, then the function is not going to change, right? So the number of neighbors where I have a different color is at most the certificate complexity, okay? This is something for you to check. So for every x, take this as an exercise, kind of to understand the definitions here. You just need to make sure you understand the definitions, and this is true. So in particular, S of f is the smallest. Okay. All right. Now, so these are all combinatorial notions. We have certificate, sensitivity, decision tree, 3 measures so far. And I'll introduce one more, then I'll stop. I don't want you to I don't want this class just to be a class of terminology. Okay. At some point, we're going to ask some meaningful questions. Okay. And not just definitions, even though the definitions are important. The last measure that we need, and I think this is why it's this definition is important compared to the others, and relations between them are important, because this new definition is algebraic. The others are more combinatorial. We're saying, okay, how many values are different from me if I change one coordinate? How many coordinates do I need to know so that the function is determined, and so on? Okay. And the last one is the notion of the degree of a function. Okay. There's a simple lemma, which I'm not going to prove, but again, I encourage you to try it, is every function on the hypercube with n-bit strings as input can be written as a polynomial of degree less than or equal. Okay, so what do I mean? So I can write an identity of the form f of x1 through xn equals, so the inputs are x1 through xn, and I can write a multivariate polynomial which exactly computes f. Summation over all subsets of 1 through n
for some coefficient Ci and then the corresponding monomial. Okay, so meaning, for example, every function on 3 bits can be written as a polynomial, which is like, let's say some constant term plus so you get the picture now.
So no matter what the function is, as long as it's Boolean, there exists real valued coefficients such that this identity. Okay, it's a representation of the function as a polynomial, right? And degree of f is, so every function can be written as something where the degree is at most n. Okay, in fact, this polynomial is unique, but the degree can be smaller depending on.
At the moment, isn't the degree to this?
So the number of terms is 2 to 10, but the degree is n,
Oh, okay, yeah.
right?
Yeah.
Because degree is just how many monomials you have. Sorry, the size of the monomials that you have. Okay, yeah.
So say
No. So it's just real arithmetic. Yeah.
so final still
We want 1 or 0. It cannot compute what?
like sum has one.
Exactly. It has to equal 1 or 0.
You can have like
You can have negative coefficients too. In fact, you can have all kinds of coefficients, but it should end with 0 or 1. There are also other notions like, maybe it doesn't have to be exactly 0 or 1, but you want it to be like less than or equal to 0.1 and greater than or equal to 0.9. Okay, you can define all of these things, but the exact thing is what we are looking at. Okay, so
The degree of the function is
okay, so such a polynomial representation is always unique. And whatever is the degree of this polynomial, that's the degree of the function. Okay, it's another measure of simplicity. Okay.
And let's do a couple of examples. So one example, or maybe let's do the example of R. So how can I write R as a polynomial? Right, so R of n should be 1 if there is at least 1 bit which is 1 and 0 otherwise, right? So what would be a polynomial representation for R? Let's say I want R of x1, x2, all the way up to xn.
This one way would be like you said, you only use the terms of n degree. So you can use all the terms that have. Oh, actually, wait.
Actually, maybe let's do something simpler first. I think it's just the negation that can be confusing. So let's say we're doing AND. So the assertion 1 minus product of all xi, almost, it's basically 1 minus product of 1 minus xi.
Okay. Right, so if I take that polynomial, that is a polynomial. Now, whenever any of the xi's is 1, it evaluates because it zeroes out everything. If all of the xi's are 0, I get 0. Okay.
And similarly for and, I could just take the polynomial, which is x1 times x2 all the way up to xn. Right, so if any of them is 0, I get 0. If all of them are 1, I get 1. So the degree here in both cases is n. Okay. Right. So degree of R n is actually n. Right. And the one other thing that is, again, something for you to play with in the definitions and figure out is that following. For any function, the degree of the function is actually smaller than the decision tree complexity of it. All right. Okay. So the picture as we have it currently stands something like this. CC is at most, sensitivity is at most certificate complexity, is at most the decision tree complexity, is at most the certificate complexity whole square. Okay. And in between, we have this sort of other branch, which tells you that is at most degree of f. Okay. And the way to prove it is basically, you take your decision tree on any path. You can write whether you reach that leaf or not as a product of terms along that path that add them. Okay. I mean, for us, it's not that important to figure out how it's proved, but we have all of these sort of relations between these measures. Okay. So degree can be much smaller than decision tree, but currently we don't know how big the gap is. Is there a function whose degree is 10, but decision tree depth is growing with n? We don't know yet. Okay. We don't know yet, meaning I haven't stated it. We don't know the answer. It's not an open question. Okay. And just like this, there are also other measures you can define, like randomized decision tree. Okay. Here, randomized decision tree just means that, I have a distribution over decision trees, and I just want my distribution to compute the answer correctly with high probability. Okay. I can also have the quantum decision tree complexity. Okay. And this is actually important because, in some sense for quantum algorithms, especially, most things that we know fit into decision tree framework. Okay. So unlike classical algorithms, decision trees are more powerful in the quantum world. So you have all kinds of measures like this. But it turns out that people have figured out over the years how all of these things relate. And what we know is, we have this taxonomy and jargon of all of these measures, the randomized decision tree, quantum decision tree, certificate complexity, the degree, which is analytic. These are all combinatorial. Quantum is, of course, bringing in quantum algorithms in there and so on. All of these are within polynomial factors of each other. Okay, this is not a single paper which proved this. Basically, we know some of these relations, and at some point, someone figured out that degree can be related to randomized decision tree. And then randomized decision tree can be related to decision tree and so on. Okay. So in particular, this implies, for instance, that so we know this, but the following is also true. Okay. And surprisingly, here, quantum decision trees are not that powerful.
quantum decision trees is a powerful model, but the biggest gap between this and this was some constant, fixed constant. If you know Grover's search, that's basically saying that the quantum decision tree complexity of R function is square root n as opposed to n. That's exactly what Grover's search is. So you have all of these intermingling things, but there's one measure which is missing here. Sensitivity is not there in this list of things which are all equivalently related to each other. Okay. So what is missing is sensitivity. Okay. So even after we're spending a lot of time, it wasn't clear how small sensitivity can be to any of the other measures. If you related it to one of them, the others are all related. So we kind of close the circle and relate everything to each other. The gaps we are kind of interested in are things like, one measure is log n, whereas the other is root n. It's like an almost exponential gap, right? So this theorem is saying for all of these measures, nothing like that is ever going to happen. Okay, the biggest gap you can hope for is maybe something like n to the 1/3 versus n, but not exponential gaps. Okay, all of these polynomial coefficients are also like extremely well searched and researched. Okay. So the one missing measure is sensitivity, and that is what became known as the sensitivity conjecture. Formulated by Nissan and Szegedy in 1989. Okay, so we already saw that sensitivity is smaller than these things. We kind of need the reverse relation, and that's what they conjecture, that degree of f is at most sensitivity to some power c. That you cannot have exponential gap between the gaps. And if you prove this, because of this intermingling relations between all of them, this would tell you that degree is the same as decision tree, more or less. Degree is the same as quantum decision tree, randomized decision tree, and so on. Okay. So this was open for almost 40 years, but then was solved in 2019. By Hao Huang. Who actually graduated from UCLA as a PhD student. Okay, so degree of f is at most sensitivity of f squared. Okay, so that's what he proved. And this S of f, the square relation is actually tight. All right. I'll talk about the tightness example later on, but after the intro of everything, we're just going to focus on these two things, degree and sensitivity. Right? How do I relate these two measures? And there's a lot of motivation behind studying these measures, which I'm not getting into. But even just the statement should be surprising. Right? Sensitivity is a very brittle kind of seeming notion, right? You change one coordinate, does the function change or not? Whereas degree is this algebraic notion. You're doing real arithmetic. So how can you relate the two together? Okay. And okay. So the way this was proved was basically the following. In
1992, Gottsman and Lineal looked at this question of sensitivity, degree of F versus sensitivity, and found a graph theoretic formulation of equivalent formulation of this question. Okay. So they postulated a graph conjecture that is equivalent to sensitivity conjecture. Okay. So in some sense, I could have just stated this seemingly very simple graph conjecture and we could have proved that. But I wanted to also give some motivation for studying this graph conjecture. So the graph conjecture is a standalone thing. How it implies the sensitivity conjecture is it's not that complicated. You just had to work through the definitions in some sense. But the conjecture is also, again, very simple to state and kind of surprising. Okay. So what is this Gottsman lineal conjecture? Or what did they actually show? All right. So to understand what they showed, let's go back to the hypergraph. So this is the magic of analytic methods, right? If you look at sensitivity conjecture, it seems like I'm doing some degree versus sensitivity, algebraic to combinatorial. Maybe I can do something algebraic, but then you come back to the graph conjecture, it has no algebra, nothing in it. But then the proof of that is going to use analysis. Okay. So it's mixing all kinds of areas in a very surprising way. All right. Okay. So let's say, this is what we have. This is the hyper cube on H3, but we have the general definition, right? Now, it's a fixed graph, right? Now they said, okay, I allow you to pick a subset S of some size. The size is important, but let's say I give you, say you have to pick at least some number of vertices, 10 vertices, 1,000 vertices, whatever you have. Okay. Pick a subset such that when you restrict the graph to vertices in S, the max degree is small. Okay. Somehow, let's say I tell you, pick a subset of 3 vertices here so that there are as few edges among these 3 vertices as possible. Okay. How am I quantifying as few edges? I want the maximum degree of any vertex within this subset to be small. Okay. So it's like asking you to find as many vertices as possible, which are very few edges. So for example, let's say I ask you to find 4 vertices here, which have as few edges as possible. Which 4, would you pick? Yeah. Right. If I pick a plane, then what's the max degree? 2. Okay. And the number of edges is 1, 2, 3, 4. But you can do better. Sorry? No, you have to pick at least 4. You have to pick 4, and then I'm asking you to minimize. Like, say you have to pick at least some number of vertices, but pick them so that you get as few edges as possible. In particular, I want the maximum degree of any vertex among the things that you pick to be as small as possible. Yeah. Right. So for example, if I pick, let's say, these guys. Okay. Then, yeah, there are no edges at all. So the degree restricted to S is actually 0. This is for 4. So for 4, I can get the max degree to be 0, right? How about 5? Can I get the max degree to be 0? So I start with these 4. Now, if I add anything, suddenly the degree is becoming 3. Right? So this almost seems unavoidable to get 3. Right? There is this sort of jump that's happening. At 4, I can get no edges. Once I get to 5, somehow at least one vertex must have a lot of edges. Okay. Like, no matter what I pick, this vertex, I'm getting 3 edges. This vertex, 3 edges, and so on. Right? Okay. So this is the question that they asked. My goal is I give you a budget on how many vertices you need to pick at least. What is the best way to pick them so that you have as few things as possible? Okay. So let's just make it a little formal. We'll introduce some definitions. For a graph H, okay. And the graph need not be regular. You're just looking at the maximum degree of any vertex in H. Okay. All right. So what did Gaussman and Lineal say? They said, take a subset S of Hn of size exactly half plus 1. Okay. So if you go to this construction that we just said, I can pick 4 vertices such that there are no edges. The same thing actually generalizes to n, any n. Okay. I can always pick 2 to the n minus 1 vertices which have no edges between. Okay. So remark, for n equals 3, we found 4 vertices such that delta of H was 0. Okay, so H, where H is graph restricted to S. You found an S which has 4 vertices such that the max degree is 0. In fact, there are no edges at all, right? My claim is, in general, we can find S of size 2 to the n minus 1 such that the corresponding graph, subgraph, has no edges. Any guesses as to what this graph might be? Yeah.
So just like.
Exactly, right? So the pattern here was that we picked all the strings which have an odd number of ones, right? Why is that good? Because when I flip a single coordinate, if I was odd, I would go to even. So I would not have a neighbor between, I would never have an edge between 2 odd vertices, okay? So for example, S equals all X such that number of ones in X is odd. There are exactly half of them. So I can find 2 to the n minus 1 vertices as if there are no edges. Okay. They asked, what happens if I ask you to pick one more vertex than this bare minimum? Okay, so 2 to the n minus 1, I get 0 edges. Pick one more. What is the least number of, what is the smallest max degree you can get? This is the budget 2 to the n minus 1 plus 1. What is the best you can do? Okay. And what they said is if imagine you proved a theorem that said any such graph with 2 to the n minus 1 plus 1 vertices, subgraph of the hypercube, this 2 to the n minus 1 plus 1 vertices must have a vertex with degree some g of that. Now, whatever this function is, this could be some function that you're trying to find. Maybe it's even possible to get 0. You can rule that out relatively easily. But maybe you say, once I go up to 2 to the n minus 1 plus 1, I need to add some number of edges. Okay. This implies that for every function f, so whatever lower bound you can show here, the same translates to the sensitivity. There's some connection between this graph theoretic statement about finding sets S which are big, but have as few edges as possible, and the trade-off between sensitivity and degree. Okay. So this is the sort of lever that we'll use to prove the sensitivity conjecture. We'll come back to the proof of this, but just understand this as saying for now, if I can show that any subgraph, once I pick more than half the vertices, strictly more, I need to get a vertex with many edges. That's our goal. If we can show such a thing, then we make progress on the sensitivity conjecture. Okay, this is surprising, right? This is sort of, usually we think things change gradually, but here, once I add a single vertex, I go from 0 to something big. Okay, that's what we're trying to say. Yeah. It can be anything. So it's like a general reduction. If you prove this for every n, you get this for all functions. So like complete proof of the sensitivity conjecture, depending on what bound G you get. Okay. So this is the theorem that Hao Hong actually proved. That he made progress on this question of you have the hypercube, which is one specific graph. And now I want to find or show that if I pick more than half the vertices, then I need to have edges. In fact, there should be a vertex with many edges. Okay. For any subgraph H of Hn of greater than or equal to 2 to the n minus 1 plus 1 vertices. Okay. You pick strictly more than a half. At half, I can have delta of H equals 0. One more vertex, you need to have delta of H at least root n. Okay, so there's this sort of discontinuous jump. one extra vertex. No matter how you pick, you need to have at least root n. Okay. And this root n is actually typed for this one. And as a corollary, this via Gaussman-Lineal theorem from 1992 implies that for any function, the degree of f is at most s of f squared. Okay. All right. So does the statement of this graph theoretic thing make sense? You have a single graph, the hypercube, and you want to understand something about it. Even if you're starting from a single graph, it's not that immediate a statement because you have lots of options for picking the subgraph that you're focusing, right? You have to pick, you can pick any subset to focus on as long as it's strictly more than a half. Okay. You might think maybe the first thing I would try is take all of, some like the first level and then pick one vertex below. But as soon as I pick everything here, the single vertex will give me a huge degree. Okay. And so on. You can, all of this parity, everything doesn't work. Okay. Even the root n construction is a little subtle. You have to work for it. All right. So how do we approach this thing? That you want to understand the maximum degree. Okay. You want to prove a lower bound on the maximum degree. And here's a surprising thing, which in some sense we saw a version of it already in maybe the second lecture. Which allows us to bring in linear algebra to help us solve this problem. Okay. So what is this observation? For any graph G, let AG be the adjacency matrix that we already have. Okay. The claim is that if I look at the largest eigenvalue of AG, and it's absolute. So the graph need not be regular for us. It need not be regular, but it's still a symmetric matrix. So I can look at its eigenvalues. Look at the largest eigenvalue in absolute, not the largest second. We were focusing on largest second because we were looking at degree regular graphs. And for those, the first one was always like the degree. When to normalize it was 1. Okay, here we're not normalizing, it's not regular. Any graph, the largest eigenvalue in magnitude is the lower bound on the max degree. Okay, so recall if G was regular, then lambda 1 of AG was actually the degree. Okay. If you had a regular graph, then lambda 1 of AG is the degree. What we're saying is if G is not regular, then the max lambda 1 is at most the max. Okay. And if we had this is going to be our sort of way to get such a bound. We want to lower bound the max degree. So instead, we'll try and lower bound the largest eigenvalue. Okay. So once again, we are using spectral properties to reason about something combinatorial. I want to understand the max degree, but which seems like a simpler thing to understand. But instead of understanding the max degree, we're going to go all the way and understand the spectrum in some sense, the largest eigenvalue. Okay. All right. So let's prove this claim. So why is this true? Well, we need to show that lambda1 is at most the max degree, right? If lambda1 is an eigenvalue, then there is an eigenvector which achieves that, right? So suppose I had AG times V equals lambda1 times V, right? So I have some eigenvector V for the adjacency matrix, and lambda1 is the corresponding eigenvalue, right? So I have this guy here. Okay. So let's focus on the vertex which has the maximum degree. Some vertex has the highest degree. So let's say this is this vertex, I. Or maybe I star has max degree. Actually, not max degree. Let's focus on slightly different thing. Sorry. So, well, let's first understand what this statement means. Right? So we have this guy, and in particular, we should have for every I, summation over j equals 1 through n of aij times vj equals lambda1 times vi. Right? So I'm looking at the ith row. So when I multiply this row with the vector, I should get the corresponding ith entry, right? That's what the eigenvalue condition is. I have this equality for every I. Okay. Now, in our proof in lecture 2 or something, we showed that if the graph is regular, then all of the other eigenvalues are at most the degree for the adjacency matrix, and the normalized adjacency matrix, all of the other eigenvalues were less than or equal to 1. Okay. We can basically follow the same proof. So how did that proof go? It said, okay, look at the largest entry of the vector V. Okay. So suppose Vi star is the largest entry. Okay. Then what do we have? Lambda1 times Vi star equals okay times the absolute value of this. Now I claim we're basically done. This is enough to upper bound lambda1 with the max degree. How do I do that? Any suggestions? Triangle inequality, right? You can say this is at most okay. And what do we know about Vj versus Vi star? Vi star is bigger. So I can say this is at most okay. But what is this sum here? A is the adjacency matrix. So in fact, the absolute value is not necessary, is 0 or 1. So what do I get here? The degree of I star, right? So in particular, it's at it's less than the max degree of G. Right, so it implies lambda 1 is less than or equal to this. Okay. Any questions about this proof? So if you have a lower bound on the largest eigenvalue, it gives you a lower bound on the max degree of any vertex in the graph, or max degree of vertices in the graph. Okay. All right. So this is there, but then if you look at this proof, there is also, some flexibility in choosing A. This is where things get really clever. So the big plan we have is you have your graph G. I'm going to build some matrix, the adjacency matrix, and use the spectrum, the eigenvalues of that matrix to understand the max degree. Okay. Looking at the adjacency matrix was the most natural thing. But can I look at other matrices where I would have the same inequality? Can I write down some other matrices which also satisfy the same inequality? Look at this proof and tell me if there is some flexibility. Row sums are all bounded. Or something even more concrete. One thing we never used in here is that these entries are non-negative. We just use the fact that we are already having the absolute value. Okay. We just use the fact that the number of ones in the row is at most the degree, right? So the same proof actually shows the following. So just as we have the adjacency matrix, there is also this notion of a signed adjacency matrix. Okay. So we say a matrix B is a signing of a graph G. Its dimensions must be the same as the adjacency matrix. So B is supposed to be symmetric. Okay. It's a signing, meaning whenever there is no edge, you should have a 0. But in the adjacency matrix, if there is an edge, you put a 1 there, right? If I is connected to J, you have a 1. Now I give you the flexibility to put either 1 or -1. Okay, so that's the weird thing that we're going to do. So the ijth entry is 0 if I comma j is not an edge and is in 1 or -1 if an edge. Okay. So for example, let's say this is my graph. Now this is 1, 2, 3, 4. So the adjacency matrix would be 1, 0, 1, 1, 0, 0. Okay, so this is the adjacency matrix. So this is the graph. This is the adjacency matrix. But now, oops, wrong one. I can put a -1 here, and that would still be a signed adjacency. Okay. In some sense, whatever was once before, you cannot change the zeros, but once you can change to -1s as long as you maintain symmetry. Okay. Maybe I'll put this one a -1 as well. This is a signed adjacency matrix. And so is this one. Okay. All right. Now, the additional flexibility that we have is the following. So this is the lemma. B be a signed adjacency matrix of G. Then okay. So whatever we showed here, that the max degree is at least the largest eigenvalue of the adjacency matrix, also works for any signed adjacency. Okay, so if you want to be extra clever to get a better lower bound on the max degree, maybe you can pick a signing which gets you a better lower bound. Technically it can't, but it's helpful in kind of doing it in one go for many things. Okay. Oops. Yeah, we require the signed adjacency matrix to be symmetric. You can avoid it, but it's not really needed. So everything will be symmetric. So I can talk about eigenvalues and not worry about eigenvalues not existing. Okay. All right. So let me now summarize the plan, and then we'll finish the plan by pulling a rabbit out of the hat. We already pulled a rabbit out of the two rabbits, right? First, we went from sensitivity conjecture to this graph thing, which was known for a long time. But the graph thing itself seems very mysterious. But now we're saying, find a signed adjacency matrix, and we'll use that as a lower bound. Okay, that's the plan. So the plan is the following. So we have the hypercube graph, Hn, right? From this, you take a subgraph H of Hn by picking some 2 to the n minus 1 plus 1 vertices. Let's call the picked vertices S. Okay. So what we will do is show that I can write down the original adjacency matrix of Hn, let's say. So this is what I have 2 to the n columns. I have 2 to the n rows. Okay, let's talk about the adjacency matrix. So this is the adjacency matrix of Hn. Now, what is going to be the adjacency matrix of H restricted to S? How can I figure out the adjacency matrix when I, basically throw out vertices and only focus on vertices? From the graph perspective, it's relatively easy. In particular, let's say these are the columns that I'm keeping. Like, let's say these are the columns that I'm keeping. So these are the rows and these are the columns. Then what is going to be the adjacency matrix of H? So this is S. Just the corresponding submatrix, right? You don't have to worry about things not in S. You're only interested in vertices in S. So the only thing that you have to focus on is this submatrix. right? So adjacency matrices have this nice thing that if I look at a subgraph formed by some vertices, then you just have to focus on those rows and columns, and that is the adjacency. Okay, in the same way, there will be, the same applies for signed adjacency. Okay. So our goal will be to find a signed adjacency matrix Bn of Hn such that for any S of size 2 to the n minus 1 plus 1, let's call this matrix BSS. Okay. So I'm starting with this matrix Bn and focusing on some submatrix with S rows, columns from S as well. We have this. Okay, so this is what we're going to do. We'll find a single signing Bn such that no matter which submatrix that you pick, by going to some subset of rows and subset of columns, as long as the number of rows is at least 2 to the n minus 1 plus 1, you have that its largest eigenvalue is at least 2. And this would prove the theorem, right? Because it's saying that once you go here, there is a signed adjacency matrix where this is true. So the corresponding graph has max degree at least 2. Okay. And this is not true if you have 2 to the n minus 1. We already saw there is a subset where there are no edges, right? If I go to that subset, the graph would, the matrix would just be all zeros. There are no edges. The largest eigenvalue is 0. If I add single vertex, somehow you get root n. Okay. And this is where the magic of linear algebra helps. Like you're finding a single adjacency matrix, which works for all subsets. That's really cool. And where does linear algebra help? The degree of submatrices and so on is very hard to understand, but there is this magical theorem called Cauchy interlacing theorem. We'll talk about that in the next lecture, which relates eigenvalues of matrices to eigenvalues of submatrices. Okay, they can be, you don't have closed form expressions for what happens to eigenvalues when you go to submatrices, but you do get some interrelations between. If you tell me the eigenvalues of the big matrix, I can give you some bounds on how big the largest eigenvalue here is. Okay, this has been known since the time of Cauchy, is like 300, 400 years old. Okay, at least. And we're going to use that to understand and prove this theorem. Okay, so there are two other things that we have to do. We have to figure out how to get this Bn, and also how to relate eigenvalues of big matrices to submatrices. Okay, yeah.
Is this the only?
Yes, this is the only known way.
There's no like way and look at.
No, I think people tried that for a long, long time. And even this, as I said, the first rabbit was going to Gaussian lineal, and then trying to use this measure itself is somewhat, it's not intuitive. But someone had this brilliant insight that, you should look at the signed adjacency matrices. And then why signed? Not very clear. But then you use linear algebra to prove this. Okay, so yeah, it's kind of mysterious that it works, but there is in some sense, a heavy hammer here, which is the interlacing theorem. Okay. All right, we'll talk about this in the next lecture, and we'll see where we go. Okay, remember the exam will be out tomorrow. I'll respond to questions on EdgeTime, but make sure they're private. You're not allowed to talk to each other while doing the exam. Okay. It's a take-home exam, basically.